right. All right, can everyone see my screen?
Yep, all good.
All right. What's up, guys? I'm Lewin. I'm going to be doing the third and final day of the Night Hacks Foundation Exam Workshop. So today we're going to be going over bitwise, base conversion, heaps, tries, and hashing. I believe that's on the itinerary. So feel free to just unmute and ask me any questions or drop any questions in the chat. If I'm like ignoring the chat for a long period of time, yeah, feel free to like unmute and like yell at me. And yeah, it's it. So we'll get started with bitwise, and let me see, 43. Yeah, I think it's a good number to get started at. All right, so bitwise operators. So every integer in C is stored, has a binary representation, and that's how it's actually stored inside the computer. So there's 6 different bitwise operators that allow us to analyze and look at these bits or the binary values of these numbers. So to start, we have our AND operator. And this works exactly as the 2 ampersands operator that we have in C with the Boolean values, except now, instead of having Booleans, we have the bits, which are either 1 or 0. If it helps you, you can visualize a 1 as being true and a 0 as being false. So, and then the AND will work like it would with a Boolean. So like, let's say we have true, or we have true and true. That's going to be true or 1. We have true or false, true and false. That's going to be false or 0. And then same thing, vice versa. And then false and false is going to be false or 0. And then same thing for the or. You can treat them as if they were Boolean values, where 1 is true and 0 is false. And so, you know, you have true or true is true, true or false is also true. And then you have false or false, which is false. As well as this in C. So for all the foundation exam questions, they actually write out the logic for if statements. So they'll say does not equal 0, or they'll say equals 0. But in C, you can actually just have an if statement. And then inside that if statement, you can have a non-zero value or a 0 value. And then the non-zero value will, this looks like an S. Hold on. This is a number, guys. All right, yeah. So the non-zero value will be evaluated as true, whereas the 0 value is going to be evaluated as false. But they do, like on all the solutions, just write it out as in does not equal 0 or does not equal false. So you can do it that way, but I would say better safe than sorry. So next we have our exclusive or XOR, and this basically just checks if the 2 inputted values are unique. So we have a 1 and a 0. That'll be unique, so that'll return true. And we'll have a 0 and a 1. Those are like unique. They're not the same. It'll return a 1. But then for values that are the same, like 1 and 1, or 1 XOR 1, or 0 XOR 0, these are the same values, so it'll return a 0. And then continuing on to some more bitwise operations, we have our not operation. So this basically just flips all the values of the binary representation. It's a 1's complement. It's not a 2's complement. So don't add the 1 like you would if it were 2's complement. Just flip all the values. That's it for that one. Then we have our left shift, which takes the number on the left of the 2 arrows and it shifts it to the left. It shifts all the bits inside the number to the left k times, where k is the number on the right of the 2 arrows. And so what that does in integer terms is it just it just multiplies the number by 2 to the k times, again, where k is the number on the right of the 2 arrows. So let's say if we have 2 and we shift it 1 time, it's going to divide it by 2 1 time. So 2 to the 1, and it'll give you 4. Or another way to look at it is you can write it the number out in its binary representation, and shift the bits to the left one time. So this is a binary representation of 2, and then you shift all the bits one spot to the left because we're shifting one time. And then this is what your binary representation will look like. And then you can evaluate this and to 4. And then same thing for the right shift. Is now it's still the number on the left of the 2 arrows is going to be shifted to the right. K times, or K is the number on the right of the 2 arrows. And this basically divides it by 2 instead of multiplying by 2. So if you have a number that is 2 and you're shifting it to the right one time, you're dividing it by 2 one time. So it's 2 divided by 2 is going to give you 1. Or again, you can write out the binary representation and just move all the bits over one spot to the right. Any questions? Oh yeah. All right. So for permutation, I was unfortunately I didn't have enough time to prepare anything for it. So we are probably not going to cover it. But on the bright side, there is no bright side. We're not going over permutation. Sorry, guys. All right.
If I will try to find good resources for permutations and go ahead and get those posted out sometime tomorrow. I know that is the day before the exam, but that's the best I got because I'm currently on the road right now. I'm a bit busy today, but I'll try to get that out tomorrow if I can find anything that's really cohesive and good. So I'll try my best, but no promises.
You heard him. All right, moving on. So now we got some bitwise problems. All right. So first one. So a good strategy for bitwise problems is they're going to give you a set of information, and you want to take that information and find how it can be represented in a binary representation. And then you're going to take any patterns you can find with this information and see what operators you can use to identify these patterns. And then you just take that and you put it into code. So let's use this problem as an example. So we have an organization with 30 groups of employees labeled as groups 0, 1, 2, 29. So I immediately can already tell that this is going to be represented as a binary number because it's 0 to 30. That's going to be the number of bits that a number can have. Each individual employee is assigned to some subset of those groups. The set of groups to which an employee belongs can be stored in a single integer called the employee's access code. So however many groups our employee is in is stored in the employee's emp code based on the bits of that integer. For example, an employee in groups 0, 3, 13, and 18 would have access codes 2, 0, plus 2 to the third, plus 2 to the 13, plus 2 to the 18. So here they're literally just telling you that the binary representation of the number is you're going to have a bit on in the 0th place, a bit on in the 3rd place, and a bit on so on in the 13th and the 18th place. Okay. Here's the eraser. Okay. All right, going on. There are several shared drives at the organization. Each shared drive is accessible by any employees and a specified set of employee groups. The access code of the drive is specified to a shared drive. Then that drive's access code is 2 to the 2nd plus 2 to the 3rd plus 2 to the 6th. So we have a one employee code that has the groups that the employee is in, and then we have several drive codes, and each drive codes can be accessed by anyone in the group of its binary representation. So we want to write a function that takes an employee's access code, M code, as a single integer, and an array of integers, drive codes, storing the access codes of every shared drive in the organization. And the length of the array, num drives, returns the number of the shared drives that the employee with the given access code has access to. All right, so first thing, we want to just find the pattern. So we know that we can represent our employee code, and the way that we represent that in a binary representation is we just take the groups that it's in. So let's say we have an employee that's in group 0, group 2, and group 4. And then we have a drive that people in group 1, group of 2, group 1 and 2 can access. So here, we want this because we know that since our employee is in group 2 and our access code can be derived or can be accessed by people in group 2, we want it to be true that this employee can access this drive code. So we can look at the combination of the numbers and see what operator that matches to. So we know that for, let's say, this pair of groups, we want this to give us 0. So we want 1, 0 to give us an output of 0. We want 1 and 1. Since this is a matching group, we want this to give us an output of 1. And then we have 1 and 0, which is already, we have that over here, but we also have 0 and 0. And we want this, since this isn't a matching group, none of these groups are on, we want this to give us an output of 0. So does anyone know what operator can give this? And yeah, you guys are already spamming it. All right, yeah, you're on it. So yeah, an and operator. Ignore the terrible ampersands. I was trying to practice how to write these, but you know, you guys know what I mean. All right, so yeah, all we have to do is just and the two integers together, and they'll give us the output of our code. So every time that we and an integer and it gives us a non-zero value, we can go ahead and assume that that employee has access to that code. And then anytime that it has a 0 value, we can go ahead and assume that the employee does not have access to that code. So first thing what's the first thing that we want to like declare when writing this solution? Yeah, account. So we have an integer called count, set that equal to 0. And then what do you want to do next? Oh yeah, sorry guys. Yeah, for loop. So then we can loop through our drive codes. Actually, we don't actually need brackets. It's going to be one line. And then we can go ahead and for every drive code in num drives, we just want to end it with our employee code and see if it gives us a non-zero value. So say if employee code, yeah, so if employee codes and drive code, yeah, exactly. So if our employee code and drive codes I, ampersand time drive codes I, and we could say does not equal 0, but again, we don't have to because it's going to give us a non-zero value and it's going to be evaluated as true in C. So we can just go ahead and end the if statement there, and then we can increment our count plus plus. Again, I would say just write it out actually, because better safe than sorry, you know. You don't want to like confuse yourself. So I'm gonna go ahead and write it out. Say it does not equal 0. And then you increment the count by 1. And then at the end, you just return the count. All right. Any questions? Can we do equals 1 instead of does not equal 0? I wouldn't do equals 1 because your number could be like greater than 1. So let's say you have 1 0 1 0 1 and your drive code is also 1 0 1 0 1. And then you add these two numbers together, you get 1 0 1 0 1. This evaluates to a number greater than 1. So yeah, you'd want to do anything that's greater than 0. All right. All right, next question. Or any questions on this so far? Nope. All right. All right, this is from what about drive code? Okay. What about drive code I and M code is greater than zero? Yes, you could do that. You could do that. Yep, that would work. Okay. All right. So this one, if you took last year's FE, you probably know this one. I think this is like the worst scoring percentage on a question ever. Like 11% of people got this. All right. So let's read it. It is getting harder and harder to stay green while using computers. Mead wrote this, by the way, if anyone wanted to know. You decided that you will reduce your carbon footprint by storing fewer bits for your integers. How you might ask? You will store your integer plus some power of two. Your goal will be to use as few on bits as possible in the resulting sum. This way you will have less bits on, and just like turning off the lights, when you leave a room, you will be saving energy and the planet. Complete the function below so that it determines and returns the least number of bits that will be on after adding a positive power of 2 to your number. For full credit, your function should take O of B time, where B is the number of bits in an integer. You are guaranteed that no positive power of 2 added to the original number will result in an overflow. All right, so first thing, this seems like a very hard question, and it is. So first thing, we can't exceed O of B time. So that's one thing to pay attention for. And then another thing to pay attention for is that we already have some code. Um, yeah, yeah. Yeah, so we already have some code. And so these are basically kind of hints. So we get num on, which is just going to be to track the number of integers that are on. Oh, sorry. Yeah. I'll let you guys read it yourselves. I'll give you like a couple of minutes. Okay. Um, Everyone good? Or just stay on the question for a little bit longer? All right. Great. Yeah, just stop me if you want to read the question if I'm going too fast. All right. So we want to, the goal, what we want to return is the number of on bits there will be after we reduce the number or make it like quote unquote more efficient. So let's say we'll take the example that they give us. We have 76, which has a binary representation of 0, 0, and then 1, 1, 0. Can I count? 0, 1, 2, 3, 4, 5, 6. Okay. And then we want to turn this into 80, where 80 has the representation of 1, 0, 1, 0, 0, 0, 0. So essentially, we're turning on a bit in a spot where it's going to reduce the total number of bits inside the number. That's what adding a power of 2 is. Adding a power of 2 is just taking any of these 0 bits and turning them to a 1 bit. Now, there's going to be a like pattern when you look at the progression of numbers to where you have more numbers than before. For like you take a number that has a lot of ones, and then at a certain point, some of those ones reset to become back to 0. So let's say if we're counting up, we have 0, 1. That this is 1. This is 2, and then this is 3, and then this is 4. Okay, and then like if you were to keep going, then you have 5, and you have this 6, 4, yeah, 6, and then you have 7, and then you have 8. So it is like anyone see the pattern here to where like when the bits drop. Yeah, that's right. Yeah. So when like you have let me delete. When you have a long number running, like a long running sequence of ones, and then you add a one to the left of it, then all those ones can drop to zero, and that'll be the next sequence in the numbers. And so that's how you drop bits off a binary number, or that's how like you use less bits. And that's the same thing that happens in the example, right? So like in the example, we have 0, 1, 2, 3, 4, 5, 6, right? And then what we do is we take the longest sequence of running of ones to the longest number of continuous ones, and we add a one to the very left of it, and that gives us 1, 0, 1, 0, 0, 0. And then we drop the two ones, and we have less bits overall than we started. And we're doing this by just adding a one, or adding a power of two by turning this zero into a one. So if we go back to the code we're given, or some of the hints, we can see that he wants us to keep track of our longest, and he wants us to keep track of our current. So we can also tell from this that we are keeping track of, the longest running of ones, and we keep track of the current running of ones, compare it to the longest, so we can update accordingly. So yeah, so I'll go ahead and write the code. Does anyone have any questions on the problem so far? Oh, all right. Okay, going into the code. So first, we already have the for loop, so I don't have to write that out. And we don't have to worry about any overflows because they tell us we don't have to worry about any overflows. So the first thing you want to do is you want to check if the current bit that you're on is a 1 bit. So does anyone know of any ways that we can check the current bit that we're looking at? Because we're going to go through the integer, the binary representation one by one. So we're going to go here and then here and then here. So does anyone have any ways? Yes. Yeah. Shift. Yep. So we can use a shift operator, and we can shift the number one, because the number one, no matter how many bits, is going to have a one here. And then we can use this to shift it to any of these zeros to check if the above number has a 1 bit inside it. So we can just shift the number one to whatever bit we're looking at to try and find if there is a one there by just ANDing it with the number. Okay, so do an if statement, and then we can do if what's the number? Our integer is x. So if x is ANDed with if x ANDed with one shifted I, because we're shifting one to the left I times for whatever iteration we're on. And if this gives us a non-zero value, so again, you could leave it like this, but I'm gonna, better safe than sorry. I'm gonna write it all the way out. If this gives us a non-zero value, then we know that there's a one in that spot of the number x. And if there is a one in that spot, you guys know what we want to do. If there is a one, because we want to keep track of the longest. Yes, update cur and num on. So we can increment cur plus plus and increment. Hold on. Increment num on. Okay. And then if there isn't a one in that spot, you guys know what we want to do. So if our sequence of like running ones, or a sequence of consecutive ones ends, yeah, we want to set cur equal to 0 because we no longer have consecutive ones. Okay. Then after you do that, you just want to check that you want to check if your current has exceeded your like maximum, or in this case, your longest variable. So just if our current is greater than longest, then we update our longest. Jeez. And we update our longest to be equal to the current value. And then after that, we end the for loop and we can just go ahead and return, we want to return the number of on bits. So we've stored the number of run it, like the longest is the longest like consecutive ones, which we're going to be removing from the bits. A number of on bits is going to be the total number of on bits. And we're adding one bit to be able to remove the number of consecutive ones. So essentially, we're just going to return our number of on bits, that being the number of on, like the number of bits that were on originally, plus one, because we're adding a bit, and we're adding a power of two, minus the longest consecutive sequence of ones, which we store in the longest value. All right. Any questions? Yeah, it's not a nice question. Yeah. All right. So that first if statement. Okay. So first if statement. We have x. So x is our integer, right? So it could be whatever case. Let's say it's 4, 1, 0, 0. And we want to check every single bit of 4 to see if there is a 1 or a 0, or if the bit is equal to 1 or 0. In order to do that, we're going to use the number 1, and we're going to shift the 1 bit, the first bit in 1 to the left, however many times our current index is on. So let's say if we're on index 1, we shift it 1 time. If we're on index 2, then we shift it 2 times. So here I'm taking the number 1 and I'm left shifting it I times, and then I'm ANDing that with our x to see if there's a 1 in that spot. So let's say I'm on iteration 3. I take the number 1, I left shift it to 3 1 time, and that'll give me the value 1, 0, 0. Then I'm going to go ahead and AND that with the number 4, because that's our integer x. And then I'll get this value, right? Because this is going to be 0, 0. And then 1 and 1 is going to return 1. And that's going to give me the value 4, which is a non-zero value. So I know there's a 1 in that location. And so I'm going to increment my current run and my total number of on. Okay. How do you think we could go about figuring out what to do in a question like this? Writing out the binary representation of numbers and figuring out how it can be smaller. Yeah, exactly. So first thing I would do whenever you get given code, you would definitely want to look at the code and see what they want you to do. It's if you look at the variables given, it's kind of a giveaway that you have to be keeping track of some longest something. So then from there, I would just write out like the binary representation of the numbers and try to find a pattern, as well as use the examples that they give you. Yeah. Miss any questions? First statement. All right. Yeah. So the return. So what we want to return is going to be the number of bits that are on inside the integer after we get done reducing the bits. So throughout this whole for loop, we've been keeping track of the number of bits that are on. We're storing 76 as the value of 8. Okay, one second. So throughout the entire for loop, we're keeping track of the number of bits that we're on. And in here, and here, we're going to take that number of bits that are on, which was the total number of bits that were on before we did anything. We're going to add 1 because we're adding a power of 2. And then we're subtracting the longest because the longest was the longest sequence of ones, consecutive ones in the number. And we know we're getting rid of that because that's our entire objective of all this code. And when we do that, that gives us the total number of bits that are left. All right, I'm still confused on how we're storing 76 as the value of 80. Okay, we are not storing 76 as the value of 80. Those are two separate integers in the example. So in the example, we get the number 76. It's given to us. And what we want to do is we want to get to the value of 80 because 80 is a value where we add a power of 2, and it has less bits than 76. So if we have 76 as binary representation, 3, 4, 5, 6, and then for 80, it's this binary representation. So this is what we're given, and then this is our desired outcome. Because we can add a 1 here and drop these bits, and then this has less bits than this. So in that example, we would have returned 4. We would have returned 2 because there's 2 on bits. 8 times size of the int for the loop. That's because of the integer size. Because you're just looping through the number of bits in the integer. All right. Anything else? One more example. Okay. It wouldn't be I is less than 8 because there could be more than just 8 bits. I'm trying to remember what the size of an int is. I don't know off the top of my head, but if you take that, multiply it by 8, then you get what?
It actually depends on your system. That's why size of is good practice. But in most cases, it's 32 bits. But in some systems, it's 64, and then other crazy ones have like some weird oblong number. So that's probably knowing me. If you wrote 8 in class, you would have docked points and go, well, the integers are different in different systems because he's very close to detail with that, which is honestly kind of cool. But yeah, size of in this case would be better just because it'll be a lot better.
So. I'll see if I can do another example, maybe if I have time at the end. But if there's no more questions on this one, I'm gonna move on to base conversion if that's fine with everyone. All right. Okay, so base conversion. So the base of a number is gonna tell you how many digits are in that number going from 0 to the base. So for example, base 10, that's our the counting system that we use. That's the decimal. So this is the common decimal counting system. So we can convert into any other base from base 10. And we do that just by dividing the number that you get by the base of the number you're trying to get to. So like if we're trying to go from base 10 to base 5, just take the base 10 number and divide it by 5 until you get to 0 and add up the remainders or like combine the remainders. And then where are the integers? Yeah. Okay. And you can also take any number and divide it into base 10 from that number by taking, here, let me write it out. So let's say we have 734. We actually got to be mindful of the number I write. So let's say we have 434 in base 5. And we want to convert this to base 10. So what we do is we take 4 as the coefficient and we multiply it by 5 to the power of the place it's in. So it'd be 4 times 5 to the power of 0, which is going to give you, 4? It'll be 3 times 5 to the power of 1. It's going to give you 15. And then it'll be 4 times the power of 5 to the 2. It's going to give you 100, I believe. And then you add these numbers together. This gives you 119, and this would be 119 base 10. And then from here, you can convert it to any other base by just dividing 119 by the base you're trying to get to. So that's probably the most common like base conversion you'll see is just take this not very large number and then convert it to another base. And you can do it that way for pretty much any number. But there are some shortcuts. Um, so if you have, so okay, let me go over base 16 and base 2 first. So base 16 is another really common base. It's the hexadecimal counting system. And so digits higher than 9 are represented with letters. Okay. Represented with letters. So A equals 10, B is equal to 11, C is equal to 12, D is equal to 13, and so on. But the great thing about hexadecimal countings is that 16 is a perfect power of 2. So converting to a binary just requires taking the binary representation of each digit and then combining them. So like, let's say, and that's vice versa too. So let's say if you want to go from, I don't know, 20 A, D, I'm not going to actually like write this all out. What you would do is you would take the binary representation of D, which would be 4 digits because it caps out at 15. You would take the binary representation of A, which would be 4 like binary digits, and then you would take the binary representation of 0 and 2, and you would take those all. You would pad these two with zeros on the left. You have 4 digits. You would take these all, combine them into one large binary number of whatever it is. And then same way, if you have a binary number, you can group it into 4. If you get one group with less than 4, pad it with zeros on the left, and then take those groups of 4, evaluate what digit it comes out to, and then you can turn it into hexadecimal from there. As well as that, you can do this with any power of 2. So octal or base 4, you would do it. So for base 4, you would put them in groups of 2 because that's the cap. That's all you need for numbers that go to 4. For octal, you do it in groups of 3 because that's all you need for numbers that go to 8. And then so on. Yeah. Okay. And then for base 2, this is the binary, and this is how everything is stored inside a computer. It's in base 2, in ones and zeros. And yeah, like I said, you can convert any base to the power of 2 into this base with the same base 16 method and vice versa. Okay, so I'm gonna go straight into some problems to like show that. So to start, we have 347 in base 10, and we want to get it to base 5. So what we're going to do is we're just going to divide 347 by 5, and then we're going to take the remainders, and that's going to be our answer. So hopefully I can do math today. We'll start over here. 5 divided by 347. So 5 goes into 34 6 times. 30 minus 4, 47. 5 goes into 47 9 times. 45. That gives us 2. So this is our remainder. We want to be mindful of our remainders. And then we take the value up here, and then we do 5 divided by 69. 5 goes into 6 one time. 15. Take that, multiplied by 3. 3 times 5 is 15. This is 4. And we take 13 divided by 13. 5 goes into 13 2 times. 10. 3, remainder 3. We take 2, 5 divided by 2. 5 goes into 2 0 times. That's our remainder of 2. Then we go backwards here, and we line the numbers up, and we get 2 3 4 2, and that'll be the number in base 5. All right. And then we have from 361 to base 10. So does anyone remember how to get to base 10 from another base? Times 10? Not quite. Number times 7. Yep, the place it is. Yeah. Nice. Okay. So we take 7, or we take 1, which is the coefficient, and here, let me go from left to right. Take 1, multiply by 7 to the 0th power, because it's in the 0th place. And this is going to give us 1. We take 6, and we multiply by 7 to the first place, and this is going to give us 42. And then we take 3, multiply it by 7 squared, and some mental math. Definitely don't have a calculator. 147. And then, because it's 7 squared, so it'd be 3 times 49. And then you just add those all together. 147 plus 42 plus 1. That's going to give you 190. That's going to be your base 10 answer. Any questions on that? All right, moving on to the next one. So, could you do modulus for questions instead of dividing? I don't think you can, because you need, so for modulus, you only get the remainder. You need this number right here as well, because that's how you keep going. Unless you have a different way of doing mod, you can use shortcut. If you know any shortcuts, feel free. Yeah. All right. So for 3AD16, this is base 16 hexadecimal, and we're trying to go to base 2. So does anyone know what's special about these two bases that we could use a shortcut for? Yeah, they're powers of 2. So what we can do is we can just take the binary representation of all the digits and then combine them into one binary number, and that's our number in binary. So the binary representation of D, so D in hexadecimal, we can go back to our notes, represents 13. So we just need the binary representation of 13. What is that? It's 8 plus 5, because it's 13. So we have 1, don't need to add, 1, 8, 0. Wait, yeah, so we can just do 1 1 0 1. Yeah, that's it. 1 1 0 1, because it's 8 plus 4 plus 1. That'll give us 13. And then we have A as well, which is 1 0 1, because A is, you go to the notes, A is 10. And then we have 3, which is just going to be 0 1. Hold on, get more space. 0 0 1 1. Okay, and then we just take these numbers and write them up here, because that's our answer. 1 1 1 0 1 0 1 1 1. That's your answer in base 2. And like vice versa, if we wanted to go from binary to hexadecimal, we would group them all into 4s, and then we would evaluate every digit and then just put them together. How would we do it if it isn't to base 2? So yeah, if it isn't to base 2, you would turn it into base 10 and then just divide it. And then from base 10, you go to the other base by just dividing it by the number. Yeah. All right. So now, any questions on this one? All right, so going to the next one. Now we have our number. a really big number. Evaluating this to base 10 and then trying to go from base 10 to base 4 would be really annoying. But fortunately, there's something special about these two bases as well that can give us a shortcut, and it's that they're also powers of 2. So again, it's the same strategy with that we just did with base 16, except now we're gonna take the binary representation. Can we convert to base 2, and then we're gonna convert from base 2 to base 4. Yeah, exactly. So if we take it's gonna be in groups of 3 because it's octal. So we don't need any more than 3 bits to represent a number. So we have 0, 0, 1 for 1. Here, I'm gonna write it out some more, try to get some more space. So here we have 0, 0, 1 for 1. Here we have 0, 1, 0 for 2. Then we have 0, 1, 1 for 3. Then for 7, we have 1, 1, 1. And for 4, we have 1, 0, 0. And for 2, we have 0, 1, 0. So it's another 2. And then from here, we can basically this is already in binary. So then now that we're in binary and we want to go to base 4, does anyone know what we would do? Group in 2, yeah, exactly. So yeah, we group. So this is a group. 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 Group. This is a group. Group. And this is a group. All right. Yeah, I'm gonna rewrite all these because kind of hard to see from there. But yeah, we have 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0, 0, 1, 0, 1. All right. Yep. 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 1, 0, 1, 0, 0, 0, 1. And then from here, we can just evaluate the digits. Okay, so we group it in 2 because, so one way you could think of it is because in base 4, our number isn't ever gonna exceed 3. And the highest that so 3's binary representation is 1, 1. So we're never gonna need more than 2 bits to represent a digit of 4. Same thing with 8, it's never gonna exceed 7. So we're never gonna need anything more than 3 bits. For hexadecimal, it's never gonna exceed 15, never need more than 4 bits, and so on. Okay. Or another way you could think of it is 4 is 2 squared, groups of 2. 8 is 2 cubed, groups of 3. Yeah. So then we evaluate the digits here. So it's 1, 0, 1, 3, 2, 3, 1, 1. Jeez. Okay. 0, 1. So we have 1, 1, 0, 3, 2, 3, 1, 0, 1. And that's going to be our answer in base. Y3? Where? Which one? Yeah. 3 is 1, 1. That's the question. 2 plus 1? Where? The last part. Okay, yeah. So these are all binary values. So we just evaluate the binary values into their digits. Yes, 2 to the 1 plus 2 to the 0 for the 3. Wait, Ash, what do you mean? Where? Nerm. Oh, you're answering the question. Okay, gotcha. Yeah, okay, I got you. All right. Quickest way to find the binary representation of a number that large. This is it. By breaking it into it's by taking each digit and taking its binary representation. If this wasn't a power of two, then you'd have to convert it to base 10 and then divide. Okay. Um, what's the part that's confusing you? Is it just the last part or
You can hear me.
mm-hmm.
Okay, so I understand that like base 0, 1, you're gonna go with the 1 and 0, 0 is a 0. Same, 0, 1 is a 1. Then you have 1, 1, how that is 3.
Sorry, my volume was really low. Could you repeat that one more time?
Yeah, I think I'm just trying to understand the math of it. Like, I
Yeah.
understand 2 zeros is gonna be a 0, and a 0
Mm-hmm.
1 is gonna be a 1.
Yep.
How you 1 and a 1 is a 3.
So for a 1, 1, we have this is in binary, right? So in binary, we evaluate the number by taking like the same way you would with base 10. So it's like we take 1 times 2 to the 0, and we take plus 1 times 2 to the 1. And then this gives us 2 plus 1. And that is equal to 3. So it's essentially for every on bit in binary, you take that value's number times or to the you take that value's place it's in and take the power of 2 to that place, and that's the value of that place, and then you add all the values of the ones in the number, if that makes sense. So there's a 1 in the 2 to the 0th place. 2 to the 0 is 1. There's a 1 in the 2 to the first place. 2 to the 1 is 2. So we just add these together and we get 3. If there is another 1 here in the 2 to the second place, that would be 4. And we add those together and we get 7. That makes sense? All right. Okay. Okay, that's it for that. And then one more in base conversion. This is probably summarize. Yes, with so powers of 2, convert to binary. That then to the desired base. For all other base conversions, convert to base 10. If not already, then from base 10 to the desired base B. Yes, exactly. Yes. Can we use this logic to convert other bases that are powers of others, like base 3 to 9? Could that even be helpful? That's a good question. I honestly don't know. I would assume no, because they don't mention it in the notes, but I mean, feel free to look into that. All right, but yeah, Joshua, that's basically the gist of it. And then yeah, this conversion is probably the simplest conversion you're gonna get. Just going from base 10 to binary. It's literally just taking a normal number, as you call it, and then getting the binary representation of it. So again, we're just dividing by 2, but it's a lot easier to divide by 2. So I'm just gonna do it in this form. Divide by 2. And this gives us, I think it's 1, here, let me write it like this. 375 is going to be equal to 2 times 187 plus 1. And then it's 187 is equal to 2 times 93 plus 1. And then it's 93 is equal to 2 times, we say 46 plus 1. And then 46 is going to be equal to 2 times 23 plus 0. 23 is going to be equal to 2 times 11 plus 1. 11 is going to be equal to 2 times 5 plus 0. 5 is going to be equal to 2 times 2 plus 1. 2 is going to be equal to 2 times 1 plus 0. And then 1 is going to be equal to 2 times 0 plus 1. And we go from the bottom up and just take all the remainders. So our number would be 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1. Make sure I did that math right. 1 second, guys. Yeah. Yeah, 1, 0, 1. Actually, I don't think I did the math right. Here, let me find where I slipped up. 11 should be 2 times 5 plus 1. Yes, it should. Thank you. And got 1. You got 1, 0, 1, 1, 1, 0, 1. That is correct. Yeah, yeah. Wait, no, it's not. 1 second. Let me redo it. All right, so 375. 2 times 187 is equal to 374 plus 1. So that's fine. 187. Subtract from, yes, you could. 5 point. Yeah, always double check your number because it's really easy to mess up. Easy math. When you take 187, it's 2 times 93, 186. Yes, 187, 93 remainder 1, 46 remainder 1, 23 remainder 0, 11 remainder 1, 5 remainder 1, 2 remainder 1, 2 remainder 0, 1. Oh, yeah. Okay. So you just fix it. That 11 error. After that, it should be correct. So it's 1, 0, 1, 1, 0, 1, 1, 1. 1, 1, 1, 0, 1. Yeah, that's the correct answer. So yeah, watch out for small mistakes like 2 times 5 plus 0 is not 11. It's plus 1. But yeah, this is correct. Wait 1 second. Okay. Yeah. Caitlin, I think if you go from the other way, you would be fine, but except you're missing a 1. All right. Any questions on how I did this?
Yeah, what do you mean? Because I did it a completely different way.
Oh, you
Like,
did? Then
I
ignore
did
that.
it, but I don't know if my answer is right. That's why I'm confused.
Oh yeah, it's not, but
Okay.
I thought you did it my way. So I was like, maybe if you went top down instead of bottom up. But if you did a different way, then just ignore what I said. All right.
Okay.
Any questions on this or how I did it or how I did it? Jeez.
So we can't just convert each digit to, like, we can't convert the 3 to its binary form and then the 7 to its binary form and then the 5 to its binary form. I'm guessing that's what Caitlin did. That's what it
Oh
kind
yeah,
of
no,
looks like.
you can't do that. Not for this because it's not a power of 2.
Oh, that's true. Yeah. Okay. Okay.
Yeah. Yeah.
Thank you. Thank you.
No problem. All right. Moving on to next topic. If nobody has any questions on this, it's gonna be binary search. Okay. Yeah, this is a quick one. So for binary search, it's just a quicker way of finding a specific number in an array or any data set. So let's say you have so number one caveat of binary search is that the array has to be sorted. If it is not sorted, you can't do this. But for binary search, you just take the left bound, which is going to be 0, and the right bound, and you add them together and you divide them by 2, integer division. So here we do 0 plus 9, we get 9 divided by 2, which is going to be equal to 4, integer division. You just truncate the decimal. And then our middle is going to be 4. And then we're searching for 23. So we check our middle number. Our middle number is 16. 16 is less than 23. So now we narrow our array to go from 0 to 4 instead of going from 0 to 9. So now we don't care about this part of the array. We only care about the array starting from here because we know that, other way around, we don't care about, because 16 is less than the target, we know since the array is sorted, the target is going to be on the right side of the array. So we don't care about the left side of the target because we know that all numbers there are going to be less than 23 because 16 is less than 23. So we move our left bound to 5, one greater than the middle, and because we already checked the middle, and we keep our right bound at 9. So now we only care about this part of the array because we know 23 has to be there. So then we do the same thing because now our bounds are 5 and 9. We add 5 plus 9, this gives us 14, divided by 2, this gives us 7. So now our middle value is 7. We check, is a number at index 7 greater than our target, which is 23? And we know that is greater than our target. So now instead of going to the right, we go to the left because we know that it's going to be on the left side of the array because we know every number on the right side is going to be greater. How do we pick a middle of the array if the array has an even amount of numbers? The same way. You just do the lower bound plus the upper bound divided by 2. So yeah, so here we do that, and we know 56 is greater than 23. We know the values are on the left of the array, so we don't care about the right side of the array. We move our bound to 6. And then we do 5 plus 6, 11 divided by 2. And that's going to give us a middle of 5. So we check index 5, which is going to be 23. 23 is not less than our target. It's not greater than our target. So that means it is our target. We found the number. I haven't seen like any binary search questions in specific. The only thing I've seen is that it'll have a sorted data set, and then it'll ask you for a strategy to find a number in that like data set, and then you would just describe how you would execute a binary search. So for binary search, log n is going to be the worst case and average case, and then best case is going to be O of 1 because you could check the number and then boom, there it is.
There was also a question on SLMP runtime, which is a problem where you have 2 lists and you want to see if one element in one list exists in the other list. It's like a weird, really niche problem, but really the way you want to think about it is if we go through each element of list 1, so O n, we perform a binary search on the second list, and binary search is log n. It's n log n runtime. There was a foundation exam a while back where in the algorithm part, they just had like fill in the blank 12 runtime problems, and SLMP was one of them. So that's also where binary search comes up, I guess. They also covered it in class too. So SLMP.
Yeah, they did. That's why it's here. And then there was one question like a long time ago where you had to write the code. Yeah, so if you had to write the code, it's not the most complicated code in the world. You just do left plus right divided by 2. If greater than, shift to the right. If less than, shift to the left. Or if greater than, shift to the left. If less than, shift to the right. And go on from there until you find the target. Or you don't. Depends on what they want you to do. Okay. Yeah, I didn't really do any problems for that. You can just go straight into heaps if there's no more questions on binary search. It's not the most frequent topic to come up, but you should know it. Just remember, it has to be sorted to do it. Okay. All right, heaps. So there's 2 types of heaps. We have a min heap, which is, and a max heap. So in a min heap, So one thing about both heaps is that you need to fill them out from left to right. So if here in this one, you can see that we have 1, 3, 6, 5, 9, 8. So if let's say this 3 didn't have this 9 as a child and this 8 existed, this would not be a heap because it's not filled out from left to right. This would not qualify as a heap, even though the other conditions are met. And the other conditions are that in a min heap, the parent must always be less than its children, and vice versa. A child must always be greater than its parent. And in a max heap, it's the opposite. Parent must be greater than its children, and the child must be less than its parent. And then you can also have meeting the slides. Yes, the slides will be available after this is over. Heaps were on the last FE. Or chances that heap is on FE, probably pretty good. Yeah, they're pretty frequent. But you never know. Always just prepare for everything. So, all right. So you can have array representations of heaps. Wait, sorry, did you say that picture wasn't a valid min heap? So the picture is a valid min heap, but what I did was, let's say if this 3 doesn't have this child here, like the 3 only has one child, but this 6 has a child, then it isn't a valid min heap because it's not filled out from left to right. Okay, so oh yeah, heaps have a array representations as well. You can represent them inside of an array. So if you're given a heap in an array, just know that if you take a node, its child is going to be equal to 2 times its index, but that's its left child, and 2 times its index plus 1 for the right child. And for the if you take a number in an array to get its parents, it will just be I divided by 2, integer division. Okay. All right. Are there multiple ways to represent the same min heap? I'm not sure what you're asking there. Like, could you have, if you have like the same values in a min heap, could you arrange them like tree in different ways where it's still a min heap? Yes. If that's what you're asking, then yes. Same thing with the array. But I don't know if that would qualify as the same min heap. Wait, sorry, could you show how to get both children and parent again real quick? Okay, so parent, so if you want to get the child of a value in an array, it's just 2 times the index of the array. So index 2, 6 is at index 2. So we just do 2 times the index, which would give us its left child. So 2 times 2 is going to be equal to 4. And we know that 4 is 9. So whoa. Huh? Oh, right. Sorry. Okay. So the way Guha does it, the way it's done in Guha's notes, who makes the foundation exam, is that you don't have a value in the parent node, right? So there's no 0 value. So you don't have to worry about 0 indexing. So for like, if you were to like Google this on how you would do it, it would always say to do +1 or -1 based on situation. But for us, we don't have to do that because there's no value in the 0 spot in the array. So I'm just gonna make a separate array to show it. But like, let's say you had, or actually there's a problem. There's a problem where it shows it with the numbers made. So we'll just do that. But yeah, you would do 2 times I to get its left child, smaller values in left subtree, greater values in right subtree, true, right for heaps. No, it doesn't. So that's the thing about heaps. You can have smaller values left or right. Yeah, it doesn't matter. As long as they're smaller than the parent. Okay, so yeah. We'll show an example of it in a second here, but yeah, 2 times I for its left child, 2 times I plus 1 for the right child, and then I divided by 2 for the parent. Okay, So 2 times I left child, 2 times I plus 1 right child, I divided by 2 parent. All right. Any questions there? Okay. And that's how you get the value in an array in a heap. Yes, yes, you can. And also, if you yes, it would be in this example, and that's because this example is 0 indexed. But on the foundation exam, it's not going to be 0 indexed. You don't have to do the +1 for the left. It's just 2 times I. Thought 2 times I just didn't work. 2 times I didn't work on this because I took this picture from the internet, and they do it in a different way than we have to do it. I divided by 2 is for the parent. Angry heaps. Good, great. But yes, this is, I think, off of Geeks for Geeks, where it is 0 index. You do have to add, do +1. But trust me, it's in his notes. You don't do that for us. It's just 2 times I, and then 2 times I plus 1 for the right child. All right. Yeah, yeah. Children of node I are 2 times I and 2 times I plus 1. Yes. Yes, this is for min and max. 2 times I plus 1, I divided by 2. Okay. If it's in an array. Or if you forget that, you can always just take the array and build a heap from it, and then just do it that way if you want to do it like that. Okay. So heap operations, we have inserting into a heap. So I'll just draw these all out. 1 second. Grab a drink real quick. Okay. So for heap operations, let's say we have a tree. So for inserting, so we have a tree. Get rid of this. Let me get some values. Just any numbers. All right, so let's get 2 at the root. 2. We'll have 6 on its left. Actually, we'll put 14 on its left. We'll put 6 on its right. It's going to be a min heap. Make 88 a child. 14. Hold up. Remember, you got to go from left to right. Yeah. 88 child of 14. We'll make 29 a child of 14 as well. All right, so let's say, what value do we want to insert into this? All right, we want to insert 1. Great. So what we would do is we would insert, because we're going from left to right when you fill out a heap. So in the next vacant spot, you would then place this 1. And then from here, you're going to percolate up until the heap conditions are met. So right now, we just inserted the 1. Are the heap conditions met? Nah. So yeah, we're going to percolate up. So we're going to swap this 1 and 6. All right, now we're the heaps. Yeah, heap conditions are still not met. So then we can go ahead and swap these 1, 2, 6. Heaps, I've seen more tracing than I've seen coding. But we are going to do some problems anyway, so you'll see. But like, yeah, you also have to code. So both. Just be prepared for both. All right, so now are the heap conditions met after we percolated twice? Yeah, so then we're done with our insertion. And so this is going to be an O of log n operation because the height of a tree is log n. In the worst case, it's going to be that in the average case, and then O of 1 in the best case. And then For delete, all right, we'll do delete next. So you're always deleting the min or the max in a heap. So you're always deleting the root. And so what you're gonna do is you're gonna swap the values of the last node in the heap. So what's the last node in this heap? 6, right? So yeah, we swap 1 with 6, and then we delete the last value. Wait, I didn't swap anything just now. Okay, yeah. So we swap 6 with 1, and then we delete the last value. Okay, and then from here, what we're gonna do is we're gonna percolate down until the heap conditions are satisfied. So right here, are the heap conditions satisfied? You always swap the root first. Yes, because you're always deleting the root in a deletion. So to delete, you just swap it with the last value, and then yeah. So heap condition satisfied here for this or not? Nah, yeah, because 6 is greater than 2. So what we want to do is we want to percolate down. Also, when you're percolating down, let's say if this was 20, we would want to, so now both of these failed the check. They're both less than the root. We'd want to do is we want to percolate down the minimum. So we'd pick the smaller value, which is 2. And so we would swap these 2, and then I'm gonna change this back to 6 because that's what it was originally. And then now are the heap conditions met? Yeah, so then we're good with our deletion. All right, any questions on deleting? No? Great. All right, we'll go over to make heap. And then, yeah, this is also going to be a O of log n in the worst case. So we have to cover the case of being more than both children. Yes, yes, because then you take the minimum of the children. Yep. Excuse me. All right. So now we can, but yeah, same thing as insertion, just O of log n in the worst case. All right, so now we make a binary tree of, I don't know why this text became black when I exported the PowerPoint, but it's fine. Just let me know if you can't read it. All right, so now for make heap, let's say we have, delete this. All right, so let me get some more numbers. They can all be random this time. 29, 29, 9, 92, 177, 13, unlucky, and we'll take 2001, I guess. That'll be the last one. All right, so 2001. Yeah, I meant put his birthday. All right, for 2001. All right, yeah, so now you build the tree, and you just go from left to right, starting at the first value. So the root is going to be, and this is how you like make a heap. So you would then do 29, and then the left child is going to be the next element, which is 9, and then right child is going to be 92. Left child is going to be 177. Right child is going to be 13. And left child is going to be 2001. All right, so then from here, what you do is, because it's obviously not a heap, you're gonna go. This is min. Well, actually, do we want to do min or max for this? Doesn't really matter. All right, yeah, we can do max. Okay, so it's gonna be a max heap. All right, so here now you're gonna go from left to right, starting at the last node, and you're gonna put it down if that last node is not in the right spot. So starting at 2001, we're gonna check its children, except doesn't have any children. So we don't do anything for 2001. So we go to 13. We check its children, has no children, and that's gonna keep going until we get to the first node, because we're going backwards, that has a child. Which is gonna be 92. All right, so now since this is a 2001, do we have to percolate down, or is it fine where it is? Yeah, we have to percolate down. Yeah, because it's less than its child. So 2001, 92. Okay. So now 92 has no children, so we're done checking there. So now we go to 9. All right, 9. Do we have to percolate down or percolate down again? Yeah. So we take, since it's a max heap, we percolate to the max. So we go ahead and because it fails both of these. So it's just 177, 9. All right, so 9 is now good. And then we go to the root. Do we have to percolate down here or no? Yeah, one more. And then we percolate to the max side. It's a max heap. 129. And then we check the 29 again. Do we have to percolate down? Yeah. So then, wait, it was 29 and 92, right? Yeah, so 92 goes here and 29. And then we're good now. So now after that, our heap has been built. And then this is an O of N operation. All right, so then heap sort. So for heap sort, you basically just make the heap. So you take the values, make the heap, do what I just did, and then you just keep deleting the root and putting that into an array until your heap is gone and it's in an array. Does that make sense? Great. All right. And that's n log n term. All right, we can do some heap problems now. All right, so see now it's one index. We don't, sorry. Can you give a quick explanation on heapify? The last one, was that pretty much right? Yes, that was it. The one with the make heap, that was just it. Yeah. So sorting is just deleting till it's in. Yeah. So after you've made your heap, you just keep deleting the root because that's either going to be the max or the min, and you put that into an array until you no longer have a heap. Just keep deleting. Yeah. All right. So does anyone remember how to find the left child of an index in an array heap? Yeah, 2 times I. So what we do here is, wait 1 second. Yeah, all right, so what we do here, we multiply by I. So 13 is at index 3, so we do 2 times 3, it's going to be equal to 6. So the left child of 13 is 19. So anyone remember how to do get the right child? Yeah, you can draw it. If you forget, just take the array and draw a heap and then go that way. Yeah, 2I plus 1. So we take, where is 16? 16 is here to index 4. So we do 2 times 4 is equal to 8 plus 1 is equal to 9. And that's going to give us index 9. So child is going to be 20. And then how do we find the parent? I divided by 2. Right. So we take 24 to index 7. 7 divided by 2, integer division is going to be 3. Wait, is it? Yeah, it's going to be 3. And that's going to give us index 13. All right. Okay, and then moving on, consider the following tree. Is this a valid min heap? Justify your answer. Is this a valid min heap, guys? Not valid? Why is it not valid? A 71, yeah, exactly. It's missing a node here, so it's not a valid min heap or whatever value would be. Or if there was a node here, then it would be valid, yes, but it's not a full tree. Correct. Great. Okay. All right. So here we have our. Here, I'll just read the problem, and I'll give y'all a second to read it. So we have consider a min heap stored in an integer array int heap array 100, which is globally declared. Complete the percolate up function below that takes an index and performs the full percolate up operation for the item at that index. While writing the code, you can assume that there is a swap function available for you that is described below. Okay, so it's mostly just fill in the blank. Do they put array versions of heap a lot on these? I don't know about a lot, but I would expect them. It would be a good thing to remember. All right, so for percolate up, that's if, like, let's say we insert a node at the bottom, and then we want to percolate up until the heap conditions are satisfied. And this is a min heap. So what are the conditions of a min heap besides the tree being full? Does a child have to be greater than or less than its? Yes, child got to be greater. All right, so this very first check, what do you guys think it should be? This very first if statement. Yeah, the index is greater than 1 because we want to stop after we get to the root if we're percolating. Great. All right. So then we can see that in this very next check, we're gonna swap and then call percolate up again. So in what situation do we want to swap the nodes? If the conditions are not met, right? Yeah. If the child is greater than the parent. So we can do current node. Yeah. So let's say we take the our heap array is called heap array. Index divided by 2, because that's how we get our parent node of our current index. And if our parent node is greater than our child node, we know that this is not a valid min heap and we need to percolate up. So yeah. Yeah, let me rewrite that actually, just for readability's sake. Okay. Is it not the other way around? Index divided by 2 is the parent. Yeah. So if the parent is greater than its child, it's not a valid min heap. The parent has to be smaller than the child. That's why this is the case. When we need to get the address of the heap array using and, yes, that's coming up. What's that in between I and X? That's the D index. Index greater than 1. All right, does everyone understand? Yeah, this is still terrible handwriting. I'm not gonna lie, but we'll go with it. Does everyone understand why this is what it is? All right, great. So now, if we do that, now we want to switch the values. So our swap array is taking in pointers. So someone mentioned it earlier in the chat. We need to address the memory address of the array. So yeah, we do use the ampersand operator and the array index to swap the values. So if the parent is greater than this child, you want to swap. So ampersand. Oh, whoa, 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 whoa. Okay, I can do this. Here we go. All right, and then keep. All right, nah. Bear with me. Bear with me. All right, yeah, so we take the current index and we want to swap it with the parent index, which is going to be the same thing, index through infinity. Yeah, my bad. Yeah, is that the ampersand? Yeah, it's the ampersand. Yeah. Does the order matter in swap function? Swap, yeah, it does. It swaps the contents in the variables pointed to by pointer A and pointer B. I don't think order in this case matters because you just want to swap the values, but always read the function it gives you and swap it that way. Yeah, that is the ampersand, unfortunately. See, I wish I could type, but I can't. I gotta write. So then you just same thing here again. Gotta write another ampersand. All right, redemption. Okay, now hold on. Okay, and then heap array. All right, yeah. So then you swap those two, and then when we call the percolate up, what index do you want to call it on? Because we're gonna keep checking index divided by 2. Yeah, we call it on the new index. All right. Any questions on this one? Out of any of the three, like part problems? Nope. Is that because we're starting at the bottom? Yes. Yeah, we're starting at the bottom and we're going to keep checking our parents. We are percolating up. What does 2 times I? 2 times I is your left child. Why are we using and? Because we need pointers for the swap function. Can I see the first part again? Yes, you can. If it was max heap, then would it be like index is greater than 100 or less than? No, if it was a max heap, you're still going to be working towards the start of the array. You're just going to be checking that the parent is less than, or that the parent is less than the child, right? Greater than the child. You're going to be checking that the parent is greater than the child. Yes. How do we know we're starting from the bottom? You're always starting from the bottom when you're percolating up, and when you're percolating down, you're always starting from the top. All right. Okay, moving on to one more heap function. And this one should be fairly easier because is there a big difference between perk up and perk down? So for perk up, you only always have to check with the parent to see if you need to perk up. Whereas in perk down, you're checking both children. So there you can have more cases when you're checking both children because both of them can violate the rules. Yeah, other conditions. Yeah, you got it. All right. So for insert, yeah, we can just read the whole question. Give y'all a second. All right. Yeah, so minimum heap is typically implemented with an array with the root node minimum value being stored in index 1 of the array. Like I said, the root node is going to be stored in index 1 here. That's why it's not 2 times I plus 1. It's just 2 times I. To insert a new value into a heap, it's originally placed in the first open slot, followed by running a percolate up operation. Write a function that inserts a value into a heap in this manner. You may assume that the array is allocated to be big enough to store the newly inserted value. All right, so we don't have to worry about adding new space into the array. But when they say the value is inserted into the heap, it's originally placed in the first open slot, where do you guys think we're going to be putting our new val? At the end, yeah. So it's going to be heap indexed by cur size plus 1, because we're taking our current size and we're adding 1. We don't have to malloc anything because they told us we don't have to. If they didn't tell us, then you'd have to worry about that, but they did. So, and then we're just going to set our new val equal. We're going to put our new value there. All right. So after we do that, we just put our new value into the heap. Are we done? Nah, yeah, we need to check if we need to percolate up, and then we need to keep percolating up. Now, we just wrote the recursive way, but this has to be iterative, I believe. Let's say that. I don't know if it says that. We're going to do it iterative anyways, because we just did it recursively. So, yeah, it's going to be, so we have our while loop. So based off the last percolate function we just wrote, what should be the case for this while loop? It should run until index is equal to 1. Yeah, so while our index is greater than 1, we want to execute this while loop. Yes, well, index is greater than 1. Okay, so, geez, check. Okay, index to cur size plus 1. Yes, I do. Great catch. We don't have an index. I'm just making things up. Thank you. All right. All right. So index is going to be where we just inserted the new value. So we just inserted our new value at cur size plus 1. We know it's there. And this is a array representation of a heap. So yeah. Don't forget your semicolons. They will mark off points for that. All right, so after that, we just want to keep our while loop running while our index is not at the root. And we know our index is at the root if it's equal to 1, less than 1. So while index is greater than 1, we want to keep making these checks. Okay, so now what do you guys think we're doing after this? What's another point that we could break out of this loop at that doesn't require it to be at the root? Yeah, if the heap conditions are satisfied, yeah. So we can check if and we know we can access our parent if our heap index divided by 2 is less than heap index, because this is a min heap again, then we know that our conditions are satisfied and we can go ahead and break out of this loop. And then if the heap conditions are not satisfied, what are we going to do? Yeah, keep going. We're going to percolate up. So this time we have to write our own swap. So we can set our temp value. This is just swap logic. You set a temp, keep one of your initial values equal to that temp. Then you set your then you do the swap. You set your parent, the value you just put in your temp, equal to the value you're trying to swap. Keep index. And then you set that value equal to the temp. And that completes the swap. And then after this, are we done? Nah, yeah, what do we need to do? Change the index, yep. And what do we want to change it to? Not plus plus, because we're not going to the next index. We want to go to where the parent was. Yes, index divided by 2. So you can do the index divided by 2. And that ends the while loop. And then we just return. Oh, we don't return anything. Yeah, it's a void function. All right, is that any questions there? All right, great. We all understand this. Wonderful. Okay. Moving on to tries. All right, so tries are trees that store a dictionary of words. So tries are like comprised of trie nodes. What you typically store in a trie node is you just have your flag, which marks if that particular trie node is the end of a word. And then you have an array of child nodes. And this array is going to span from 0 to usually 26 or 25 based on the alphabet you're using. If you have like digits, it could go like longer than that, but usually it's just from 0 to 25. And then if there is a child node at the specific letter, you're going to take the index of that letter and you're going to access the trie at that index. So I'll show how you would do that in a second here when we do problems, but just know that if there's an index at a letter, there's going to be another node in that letter. If there's not, or another node at that index, if there's not an index at the letter, it's just going to be null. And then you just traverse the trie by moving down the needed letter index. And if you hit null, then you know that letter does not exist in the trie, meaning the word you're looking for does not exist in the trie. Right. Any questions there? All right, wonderful. Okay. So trie operations. You have inserting into a trie. So this is basically the same idea of what I just said. You take a word and you traverse down that word while traversing down the trie. And if you hit null, then you make a new node instead of just stopping. So you make a new node at that location and set its value to be equal to so let's say at that node, if that node was the end of the word, you would set the flag equal to 1. But if it wasn't the end of the word, then you would keep running and you would create a new array of children, and then you would make a new node where you hit null in your word. So here, let me draw it out. All right, so let's say you have a root. Your root's going to be empty. And so let's say you have the word. Someone give me a word. Cat. You have the word cat. let's say you wanted to insert a new word, car. So what you would do is you would take the string car and you would traverse across each character. So you're at C in the first iteration. So is C in the try? Yes. Catastrophe? I'm not spelling that. Is C in the try? Yes. So you go to the C and you go to A. Is A in the try? Yes, A is in the try, so go to the A. And then you check, is R in the try? Then you check if there's an R. There is no R. R is going to be null. So instead of stopping there, what you're going to do is you're going to make a new node at the letter index of R. And that's how you would insert the word. And since you're at the end of your string, you would set the flag for R equal to 1 to indicate that this is the end of the word. And it's the same thing for search, but instead when you get to, let's say, if you're searching for car, you get to here to A and R is null, then you're done. You know that car does not exist in the try and you can finish. So makes sense? Great. All right, so some try problems. The worst part of try problems is never really understanding how a try works. It's usually the coding. So for this one, it's iterative. Sometimes it'll be recursive. So just make sure your recursive coding is at your very best. Why it's confusing me? Yeah, it can be pretty confusing. Just want to just repetition will help. Okay, 1 second. Give y'all a second to read the problem. All right, so for here, we're going to write an iterative, non-recursive function that takes the root of a try and a string and returns the number of new nodes you would have to add to a try in order to insert that string. You may assume that string is non-null, non-empty, and contains lowercase alphabetic characters only. So we don't have to worry about uppercase. It's good. However, you must handle the case where the root is null. Okay, so we want to, this is a mix of search and insert, or not really, because, math exists, but we want to search for a word. And then if we get to the end of the word, then we know that we don't have to create any new nodes in order for this word to be inserted into the try. But if we don't get to the end of the word, does anyone have a way where we could immediately know at that node how many more nodes we would need to create to insert that word? Yeah,
Can you
so
say
we could.
again?
Hmm?
I missed what
Yeah,
you said.
yeah,
Can you say again?
yeah. I asked if, so we know that if we get to the end of a word, then we don't need to store. We know that we don't need to create any more new nodes to insert that word. But if we don't get to the end of the word and we can't find the rest of the word in the try, does anyone have a way that we can what's the word? That we can return immediately at that node the value of how many nodes we need to return to make the word? And someone said string length and subtract by nodes we already went through. Yes, exactly. So we use string length to store the length of the word, and then however many nodes we can find in the try, we just do the length of the word minus those amount of nodes, and then we can just return that at that point in O of 1. Okay, so what's the first thing we want to do here is create an integer or a variable to store string length, because we want to do this outside of our loop, so we don't, because it's an O of n operation. We don't want to keep running this in the loop over and over again. So get the length of the string. And then we want to go ahead and loop through our try, starting at index 0, because we've discovered 0 nodes thus far. And we want to go to the end of our word so we can use our length. All right, and then we check. So yeah, what do we check for first? Now remember, it says we do have to handle the case, and or just when. Oh, sorry, missed a question. Do we have to check if root is null first? So yes, we do. That's the first thing we check for, because we want to stop. I don't know if you mean like outside of the code, outside of the loop. We don't have to outside of the loop because we're not accessing it. But you can if you want to, but it's not required because we're not accessing the root yet. But yeah, as soon as we get into the for loop, we want to check if our root is null, because if our root is null, that's our stopping point. So if our root is null, we can go ahead and return. I don't think you would, nah. I think it'd just be fine because it works, it runs. But yeah, you could just check in here. You would lose points though if you only checked it outside and then inside the for loop you had no stopping point. Then you would lose points. But if you did both, then you should be fine. So yeah, if root is equal to null, then what do we do if our root is equal to null? Not quite, because yes, yeah, we want to return the length minus the nodes we've already traversed. Yeah, so we want to return length minus I, because I is going to keep track of the nodes we've already traversed, and then the length is going to be the length of the word. And then after that, that's the only check we need. How do we continue to go through the, all right, actually, yeah, I'll just explain this straight up because the code for this could be a little confusing. So we have our root. You can't return just the length because you want to return the length minus the amount of nodes you've already traversed. If you're just returning the length, you could have, let's say you had cat, you could have gone to C, then A, and then T doesn't exist. T is null. So at null, you need to return 3 new nodes when you only need to return 1 new node. So you want to keep track of how many nodes you visited and then subtract that from the length. And then we set our root equal to, we just want to traverse. So this is how you traverse it, children. So we take our current word character and we subtract the value A from it. And so the reason we do this is because every character has an ASCII value, right? So it'll be something like X is equal to like 72 or something. This is definitely, that's not right, but it's just an example. And so the way that you can get its alphabetical number is by subtracting A from the value, because A also has an ASCII value. And the ASCII values for characters they're consecutive. So it goes A, B, C, D, E, and it would go like 62, 63, 64, 65. So the difference in those characters is going to represent its place in the alphabet. Where did you get children from? Yeah, the struct. All right. And that's why you subtract A. And then after this, are you done? Nah, yeah. What do we have to do? Return 0, yes, because it's the case where It's the case where the word is inside the try and you never hit null. And we just return 0 if that's the case. And then we are done. Any questions on that one? Nope. All right. One second, and we'll move to the next one. All right. So wait, so root is equal to root child is saying we're adding the node? No, root is equal to root child is traversing to the next node. So this is root equal to root child. So we have, let's say, a node A. And we're looking for, let's say, node W. Can you do an example of running this code? Yes. Yes, I can. Just 1 second. So actually, this will answer both questions at the same time. So let's say our try is, say our try looks like we have all right, this is all lowercase letters. We have Adam in our try. And we have Ash in our try. And then let's say we also have like car in our try. And let's say we're given the word apple. All right, so what we first do is we store, so I guess we can just go to the code. So first thing we do is we store the string length of apple. And that's gonna be 5. So our length is equal to 5. Then we go and we run our for loop. And we're given the node and then the root. So our root is going to be this. Our root, this is given into the function. And this is also given to the function. So we check if our root is null. So our root is not null. So we then traverse to stir I. So our current I, here, let me pull the code up again. We then traverse to stir I, which at this iteration is 0. So we check the first index of the string. And that's going to be A. And so we do the ASCII value of A minus the ASCII value of A is going to be 0. So we check the children array for a node 0. And A is going to be in that index. So we traverse. Our root now becomes this node. So our root now becomes the child index at index 0 because A minus A is 0. And now our root is at root A. And then so we run our loop again. And we check if our root is null. Our root is not null. So then we traverse again. But now we're at index 1. So we're looking at P. And so we're taking our ASCII value of P minus the ASCII value of A. And that's going to be whatever P is in the alphabet. I have no idea. But here, I'm not about to say my ABCs. Okay, yeah. So whatever P is in the alphabet, we're indexing that in the array. And that's going to be, it's going to search for the P node. And there's going to be no index in that array at position or at the index that this value would give. So since there's no position there, we're setting our root equal to null. So now our root is, so now our root is equal to null because there was no child at that index. And so we run our loop again and we check if our root is equal to null. And since our root here is equal to null, we're going to go ahead and return the length of our word, and we're subtracting it from our current index, which I believe here is 2. Yeah, because we're on our second iteration and our root is null, and we're going to be returning 3 because that's the amount of nodes we need to create for the value, or it's 0 index, so we're going to be returning 1. So 4, which is the amount of words we need to create to insert apple. All right, so moving on to the next try question. So this one is, you also get ones like these where you're just creating a try and then you just have to count however many nodes there are. So for this one, yeah, as long you have to, it's 3 points. Just be careful because you don't want to slip up because there's not a lot of partial you can get here. So just just count carefully, make sure you get all your points. So there are ways to do it where you can like line them up. I prefer to just create the try and then be careful with it that way. So like here I'm gonna need space for it. But yeah, I prefer doing it. Wait, it's the wrong set. Just create a node. By the way, this empty node also always counts as 1. And then just start inserting the words. So cat cap catapult. So we already have cat, so we can just continue from here. Be careful you're not creating an extra amount of words. Catapult. And then catalyst. So we go down, CATA. Catalyst. And the next word is phosphorate. Okay. So E H O S P H O R E cent. Okay, and then pancake. Go here. Wait, what am I doing? Scroll down too far. All right, you go here. A and C. You guys get the point. And A. And then you have pancakes. You just add the S. And then you would just very carefully count up these nodes and you would get 35. And then, yeah, just make sure, be careful counting. Yes, does include the root node. Yep. And anything else? Oh, they also give partial if you're like 1 off or 2 off. So yeah. Someone just returned 0 in the last question and nothing else. Is that points? Yeah, that is points. It's like +1, +2, maybe. Okay. Any question on tries? All right, yeah. So now we're to hash tables and hashing. Running out of water. All right. So a hash table is a way that you can store and search for records much more efficiently than you would in an array. So the way you do this is by taking the keys or your values and evaluating them in a hash function, and then taking that value and storing them in your hash table. So different keys can get the same value when you plug them into your hash function. This is pretty much unavoidable. So we have different ways to handle collisions. So we have the first way is going to be linear probing. So linear probing is just going to be, if you hit a collision, go to the next spot. If that's collision, go to the next spot, then the next spot, and so on. So let's say we have, in our table, we have value like 5 and 4, then 3, and we want to insert, our hash function gives us index 0 for 6, and we want to insert index 0. Well, yay, for linear probing, there's something already here. You got to go to the next index 4, something already here, go to the next index 3, something already here, go to the next index, and then it's finally open. You can put it here at 6. Then we also have quadratic probing, which is you take your current index and you add c squared to it, where c is the number of collisions. So if you're at 1 collision, then you add your index plus 1 squared. If you're at 2 collisions, it's your index plus 2 squared. If you're at 3 collisions, it's your index plus 3 squared, and so on until you can find a way to insert your value. Okay. And then the third way is separate chaining. So this is specifically if you built your hash table to store linked lists, then if you run into a collision, you're just gonna add that value to the linked list at that spot. So let's say we have a linked list of 0, a linked list of 1, and a linked list of 9 in our table. Well, if we hit a collision at index 0, we would just extend our linked list to store our new value. And same if we had a collision anywhere else. Any questions there? Nope. All right, great. All right, so for hash function tips, sometimes you'll be asked to like evaluate a hash function to see if they're sorry, the chaining. Can you mention that again? Yes. So for chaining, if your hash is when your hash table is built with linked lists. So it stores linked lists in its indexes instead of values. So if you have, and because you do this because if you hit a collision, then you can just extend the linked list instead of doing like probing. So I'll try it out again. If you have linked list in index 1, linked list index 2, all having different values at the start. And if you had a collision at, let's say, index 0, then you can expand your index to store. So let's say we want to insert 2, and our hash function gives us index 0. Well, there's already a value there, so we have a collision, but we're building our hash table to with linked lists. So now here we then extend our linked list and set it equal to 1, set it equal to 2, the next node. No problem. Okay. On. So yeah, sometimes you'll be asked to evaluate hash functions. So a way that you could do, well, not a way that you could do this, but what you want to look out for is the like ask ways that like, what could you do to make this better, or what's wrong with this? And things you want to look out for is you want to look out for hash functions that don't work well for any type of input, especially if it mentions the input in the problem. You want to avoid overflows, and you definitely want to minimize collisions. So like hash functions that lead to a lot of the values having the same hash value are bad, and you want to avoid those as well. And then sometimes your like hash table is going to fill up. It's inevitable. So we want to be able to expand our hash values or hash tables to store more values. So what you do here is you pick a prime number that's at least twice the size of the current table. And you pick a prime number because those work best for when you're modding your hash values, because a lot of the times your hash values are going to be a lot larger than your table size. And in that case, you mod your hash value by your table size to be able to insert into the table. And this works best with prime numbers. So you pick a prime number that's at least twice the size of your array, and you change your array size to that size. Then you change your hash function accordingly. And then after that, you rehash all the values. So let's say we have an array. Busting out the ruler. Say we have an array of 5 elements. Okay. We just gotta go. We have an array of 5 elements. 2, 3. Okay. Yeah, this is 5, and it's filled with, say, our values here. I don't know why it's sorted. Doesn't matter. And we have our hash function, our current hash function. And so all these values came through this hash function and got stored in this array. So our array is full. So now we want to pick a prime number that's at least twice the size of the array. So what's a good number that we could change our array size to? 11, yeah, because 11 is prime and it's greater than 10, which is twice the size. So we could change to an array size of 11. And then yeah, and so now after this, we want to change our hash function based on our new table size. So if in our hash function earlier we were modding by 5, now we want to mod by 11. So now we change our hash function into our new hash function, and then we rehash all our values into the new table based on our new hash function. That makes sense. And this is an O of N operation because we need to rehash N values. All right. Any questions? Nope. Great. All right, so we can do some hash problems. All right, problem one. Are they going to make us do this on the exam? They might. You never know. Yeah, they did ask it in CS1. All right, yeah. So this is a lot of reading here. I'm just gonna let me give y'all a second to read this. A whole essay for 5 points. Yeah, yeah. But hey, you need every point you can get. So I don't want to waste time limit per question. All for 5 points. All right, yeah. So basically, to sum up what all of this is you have these guys that are making a hash map and they have this pseudocode implementation. They just want what's wrong with the pseudocode implementation. So taking a look at the pseudocode implementations, anyone have any ideas what could be wrong with that, with it? So reading? All right, yeah, I'm gonna give you all a second more to read. It's fair. Yours is from spring 2023. Okay. Can I scroll down past the code? Yes, I can. They gave us some long rambling words. All right. Is the issue that they never use the hash function to find the index? Let me read this. Create a hash table for each integer in the file, insert n into h. If h is num-collision is greater than 0. This, um, I think you're supposed to just assume that they did when they insert it. So that's not it's because it's destroying stuff instead of collision probing. Shouldn't num collisions be greater than so wait, so what's the goal of what they're trying to do here? They think they can loop through the input file and they can insert the integer into a hash table one by one. As soon as a collision occurs in the hash table, they must have found the duplicate integer. So they're assuming that when a collision occurs in a hash table, they found the duplicate integer and they can just destroy that integer at that index. Is that a good assumption? Yay or nay? No, right, because when you take your hash function, multiple values that are not the same can get the same hash value. So by doing this, yeah, unless they have the most miraculous hash function ever, yeah, they're going to be destroying values that are different when they're only trying to destroy duplicates. So yeah, the answer here is collision does not imply equality. That's the number one thing to know. Yes. Okay. So as long as your explanation has something that includes collision does not equal equality, you got all the points. Zoom Lansky wrote this. Hey, he needs to write more problems. We can't anymore, but okay. Suppose we have some hash. Suppose have some hash function that produces the following hash values for the following strings. Using the hash values above, insert the strings one by one in the order given above from wicked down through the dinner into the following hash table. So luckily, they already gave us all the hash values. We don't have to evaluate them ourselves. 1 second. 1 second. All right. So yeah, they gave us all the hash functions. Wait, there's some questions. Which exam is this question from? This question is specific or the prior one with all the reading? This one. This is spring 2022. 11 or 12. So it's 10. Yeah, it's 10. Yeah, because so yeah, we take our hash values. All our hash values are greater than our table. So what do we do with our hash values to be able to insert them into the table? Mod 10, yeah. By mod 10, what's all right, so we can start with wicked because we're going in that order. So what's 35,429 mod 10 is 9. It's the last value for all of them. So just go ahead and say this is index 9. This is index 2. Next one. All right, oh, and yeah, we're using quadratic probing. So now we hit a collision here at index 9. What do we do? Add 2? I don't think so.
If it's linear probing, you're just gonna go to the next empty index. If it's
Yeah.
quadratic, it's the index plus like 1 times 1 mod 10, and if 1 times 1 doesn't work, you do like 2 times 2 and so on.
Yeah.
If it's and we're just doing quadratic, and if it's chaining, you just draw a link close.
Exactly. So yeah, for quadratic, we're gonna take the amount of collisions that we have and we're gonna square it. So since 9, this is our first collision in the sequence, it's gonna be plus 1 squared. So this is gonna be equal to 10. And 10 is out of bounds. So then we take mod 10 and put it at 0. How do we know the index of that hash value? So we do the hash value mod 10, and we know mod 10 is just the last value here of the index of the number. Yeah, so you mod the length of the array. Yeah. It's not always 10 though, so it'll be a lot harder. That's why we pick prime numbers when we're resizing arrays.
That's why I was asking you, like, is there an easy way, like, mentally to do like mod 11 and mod 12 in your head without, like, somebody like me, I have to divide it out, and that takes a lot of time
I would
off the clock.
I would definitely divide it out unless you're like certain of shortcuts.
Okay.
But 10 is the only shortcut I know where it's just the last digit.
Okay, thank you.
All right, yeah. So here we get 10, which is out of bounds. So we take 10 mod 10 equal to 0. And so we know that this is now at index 0. So now we go to dinner. Dinner hits another collision. So this is the first collision for dinner. So it's 9 plus 1 squared is equal to 10. Now 10 is at index 0, and it's another collision. So we are now on our second collision. So what do we do now? Nine plus 2 squared, exactly. So 9 plus 2 squared is going to be equal to 13. And 13 mod 10 is 3. So now this is going to be equal to index 3. So we have Wicked at index 9. We have Cheesy at index 2. Lasagna at index 1. 4 at index 0. And dinner at index 3. That makes sense, everyone? Any questions on hashing or general? No? All right, well then from here, I think we can go ahead and stop the recording. I think that's the end of the slides. Yeah, I pray for mod 10 too. Am I co-host? Yeah, I can. Yeah.